Hello and welcome to EEE 41, Lecture 6. For this lecture, we'll discuss the ideal BJT analysis and also introduce the ever-small model for BJTs. Our objectives for this lecture are the following: to show the derivation of the BJT currents in terms of material properties under ideal assumptions, identify factors that affect the BJT currents and its performance parameters, and lastly, to compute the ever-small parameters and terminal currents given biasing conditions. Before proceeding to the BJT analysis, let's just recall some concepts first on how we derived the IV curve of our PN junctions. So what we did last time was to derive the excess carrier concentrations as a function of space or position. So we have here as a function of x. And this was determined from the MCDE with the following boundary conditions. So at far from the junction, the excess carrier concentration is assumed to be 0. So far from the junction, there is no excess carrier concentration, and the actual n sub p is simply np naught. And at this side, at the n side, Pn is simply Pn naught. So there is no excess carriers. While at the edges, we use the law of the junction to determine the carrier concentrations at the edge of the depletion region and use that to compute the excess carrier concentration at the edge of the depletion region, knowing Np naught and Pn naught. So we use, for example, at the P side, this MCDE form at steady state and no light, and this is the corresponding general solution, and we use these two boundary conditions to come up with this expression here, which tells us that the excess carrier concentrations decreases exponentially as you go farther away from the junction, which is shown here, the decreasing exponential. However, it looks linear since this one is in log scale. Now, using this, how did we end up with the current? So we assume that there is no RG in the depletion region, such that the injected carriers from the P side are all able to make it to the N side, and electrons from the N side make it to the P side without recombination or generation. So there is no carrier lost, and therefore the current is maintained. So Jn from this point to this point is constant, and Jp from this point to this point is constant. What we were able to determine was basically this Jn at this point, since we know delta n at x double prime. So this one was used to derive this portion here, while this one was used to derive this portion right here. And what was used was the J diff current equations. So for n-type, qdn derivative of dn with respect to dx. So since the current at this point is constant under this no RG assumption, we simply sum these two values to get the total current, which must be constant throughout the junction. So in terms of this plot right here, to get the current, what we are most concerned with is actually the slope of the carrier concentration at this point, which we use the slope to get the diffusion current. So we'll use around the same approach for our BJTs. So the analysis that we'll present in this lecture is specifically for PNP, but we'll also show the corresponding equations for NPN. So we'll assume that the emitter is at the left and the collector is at the right. the metallurgical width of the base, or its physical width, is WB, and its effective width is W. Since we now have three regions, we now define three different axes. So for the base, we use the variable x and start at the end of the depletion region. For the collector, we use x prime and we start at the edge of the depletion region, whereas for the emitter, we use x double prime and it is leftwards, starting from the edge of the depletion region. Now, we should also be careful on how these axes are related to our transistor current. So if we have our PNP, so this is the equivalent symbol of this one, and IE is rightwards, IC is rightwards, and since x double prime is leftwards, then we'll have to incorporate a negative sign in our expressions later on when we convert from carrier concentrations as a function of x prime to current as a function of, say, this direction right here. Aside from that, we'll also define some new variables, although these are just shorthand notations. So since we are considering P and P, then the doping concentration at the emitter must be some Na, and to differentiate that with the doping concentration, or specifically acceptor doping concentration at the collector, then we have here NaCe. But since it must be clear to us that we are dealing with a PNP BJT, then we can simply say or indicate Ne to be the doping concentration at the emitter, and since we have a PNP, then this Ne must automatically be referring to some acceptor doping concentration. So we simply drop the variable or the letter that indicates the doping type and let the type of BJT denote what doping or what dopant that is. So for the base, we simply use NB instead of NDB. So DE is the diffusivity at the emitter, and since we are only concerned, or our analysis is focused on the minority carriers, again we're using MCDE, then DE must be the diffusivity of electrons at the p-type emitter. So tau E is the minority carrier lifetime. It corresponds to the electrons for the emitter. LE is the minority diffusion length of electrons at the emitter. And NE naught is some NP naught, since the emitter is a p-type. So this, when we say NE naught, this is simply Ni squared over Ne. Although eventually in our analysis, we'll differentiate the Ni of Ne and Nb. Although by default, we can assume that these two regions are both silicon and therefore they approximately have the same Ni. But if they are composed of different materials, say in a heterojunction, then these two values might not be exactly equal. So for our ideal BJT analysis, we solve first the minority carrier diffusion equation in each quasi-neutral region. So this time we have three quasi-neutral regions to obtain the excess minority carrier profiles, and use different set of boundary conditions for each region. So since we have a PNP with three quasi-neutral regions, so let's consider this figure right here, where we have the emitter, the base, and the collector. And assuming that it is under LLI, then with the emitter having the most or or the largest doping concentration, then its P should be high up there, and P for the collector must be somewhere there, and the majority carrier concentration is also not strictly or heavily affected. Now we can compute the equilibrium carrier concentrations based on these values, and say we assume that both junctions are, say, forward biased. So if this PN junction is forward biased, then there must be some excess minority carriers at the edge of the depletion region. So what I'm drawing here is the expected trend or result when the device is in forward active, so or the junction is forward biased. So we have that plot for the minority carrier, whereas for the other side, if it is also in forward active, then the plot should look like this one. But what does happen, or what happens in the base? So from our usual analysis, we need two boundary conditions, and if this one is forward biased as well, then we will expect some trend like this. However, these two trends individually will only happen if the carriers die down to around 0 excess carrier concentration, which only happens when this region is long enough. But the BJT is designed such that only few carriers will recombine, and so what we will actually get is some plot like this for the case that both junctions are forward biased. So let's say we were able to get expressions for this minority carrier concentration, or specifically the excess minority carrier concentration. Our next step is to evaluate the minority carrier diffusion current. So these are diffusion currents, although instead of J, we multiply by area to get the current instead of J. So we, just like in the PN junction analysis, we evaluate it at the edge of the depletion region. So for the electron current at the emitter side, so N is based on the derivative of the excess electron concentration at the emitter evaluated at x double prime is equal to 0. So we want the slope of this thing right here. For IEP, we need the slope of delta PB with respect to x, and this is delta PB, but evaluated at the edge of the depletion region, which is at x is equal to 0. ICN is the electron collector current, and we evaluate or determine that based on the slope of delta NC. So this delta NC, we need the slope at x prime is equal to 0. And for the last one, ICP, we need the slope of delta PB at x is equal to W, or at the edge of the depletion region at the base towards the collector side. Now, if you may recall, our diffusion currents have a negative sign for holes. However, for this part here, this is for electrons, but since we are using x double prime, then we add a negative sign. So the rest are based on x or x prime, and we don't need to add an additional negative sign. Now, once we get the currents at the edges, we can just sum these two to get IP, then sum these two to get IC, then perform KCL to determine IB. Now we present here the actual analysis. So this is the MCDE for the emitter region. So for the emitter region, steady state, no light, there is some diffusion happening based on, or as when we apply some bias voltage, and there is RG happening at this point. So our boundary conditions is that the excess electrons or minority electrons at the emitter side far from the junction, x prime approaches infinity, is 0. So this one assumes that this emitter is long enough such that the excess electrons die down. At the edge of the depletion region at x double prime is equal to 0, we'll use the law of the junction, specifically using VEB. Note that the applied voltage is V sum VPN, and at this junction, the P side is the emitter, the N side is the base. For the base, we use the similar set of equations. So this time we are using x, and our variable is delta PB, so excess minority holes for the N-type base. Now our boundary conditions at this side is dictated by the law of the junction for the EB side, whereas for at x is equal to W, the boundary condition is dictated by the law of the junction at the collector base junction. For the last, the collector region, we are now writing our equation in terms of x prime and delta NC. So p-type minority carriers are electrons at the collector side. At this portion, x prime approaches infinity, the excess is 0. At x prime is 0, we use the law of the junction. So we have already set up the MCDE. We now proceed with the solution of the differential equation. So this is for the emitter, and with that form, we know that this is the form of the general solution. So we have two unknowns. It is a function of x double prime, so that we start at this point to this point, and the minority diffusion length is LE. Now our boundary conditions is that at x double prime approaches infinity, there is no more excess minority electrons, and therefore A2 must be 0. At the other edge, at x double prime is 0, we have this value right here, but when we evaluate this at 0, then e to the minus 0 is just 1, and therefore A1 is exactly equal to this term. And therefore, since this one here is A1, so we note that this one here is A1, and then multiplied by e to the minus x double prime over LE. So now we were able to show that the excess minority electrons should follow this shape when forward biased. So this is a forward bias drawing, and we use this to get the current component for electrons at the emitter side. So minus QADE, derivative of delta NE with respect to x double prime, evaluated at x double prime is equal to 0. So note that this is just a constant, not a function of x prime. We just multiply this QA DE, so we get this n naught e to the QVB VEB over KD minus 1. Derivative of this one is itself multiplied by minus 1 over LE for chain rule. So the minus sign disappears and we get this LE, and evaluated that x is double prime is equal to 0, the exponential is just 1. So we get this expression for IEN. For the collector region, again, we start with MCDE in terms of x prime. The general solution is should look the same, although note that we are now in terms of x prime, and then the diffusion length is LC. Now, the boundary conditions at x prime approaches infinity, the excess is 0, which means that A2 must be equal to 0. And so we're left with this one. This one is based on the law of the junction at the base collector junction. And at x prime is equal to 0, again, we'll get that this thing here is simply equal to A1 for this case. And so we get this A1 times e raised to minus x prime over LC. So this one should be simply x prime. Now, we differ this term right here. This expression actually tells us that the excess minority electron concentration at the collector side decreases exponentially as we go along x prime. So that's why we get this shape right here when this junction is forward bias. So next, we get the current component associated with the excess electron concentration at the edge of the junction or at the edge of the depletion region. So minus QADC, derivative of delta NC with respect to x prime evaluated at x prime is equal to 0, is simply equal to this one, which is very similar in form as the previous one, although DE became DC, LE became LC, and NE naught became NC naught, and now we are in terms of VCB. Okay, since the collector is the P side, the base is the N side. So now for the base, again, we have the same form of the MCDE and therefore end up with the same form of the general solution, although note that this time we are writing in terms of x and the diffusion length is LB, and what we're solving is delta PB at the n-type base. What makes this region more complex is that the other end is not anymore always 0. So the boundary conditions now both depend on the junction voltage at the two sides, and therefore we cannot say that A2 is 0 nor A1 is 0. So we'll just skip the actual derivation, but show that this is the resulting expression for delta PB. So there are two complex exponential functions multiplied to PB naught and the e raised to VA over VT minus 1 for the two junctions. However, we'll simplify or show some simplification for this one later on, especially when we go to the current equations. So to simplify, at least how we write the expression, note that raised to some psi minus e raised to minus psi over 2 is actually, or can be rewritten as the hyperbolic sine of psi. And the derivative of this hyperbolic sine is actually the hyperbolic cosine, which is e raised to psi plus e raised to minus psi over 2. Now we'll use this derivative later on when we differentiate this expression to get the currents. But for now, this is the equation we have shown a while ago, and what we can actually do is divide both numerator and denominator by 2, and then note that, for example, the numerator here will now follow the form of the hyperbolic sine, where this psi right here is this whole w minus x over lb. So for the denominator, the psi is w over lb, and so we just did the same thing here, x over lb, w over lb. So this is the excess carrier concentration with respect excess hole concentration at the base, which changes in shape both with respect to the VEB and VCB. So for example, if both junctions are forward biased, then we might expect something like this. If this is the equilibrium concentration at the base, if both junctions are reverse biased, then we'll possibly get something like this, depending on this complex functions right here. But say it is in forward active, such that one side, or the base emitter side, is forward biased and the collector side is reverse biased, then we'll expect something like this. Although these plots right here are the actual PB. So the excess is this plot right here, or this area right here. So again, we'll use this excess carrier concentration to determine the current. And so I've here is a copy of the expression in the previous slide, and IEP is this minus QAdB derivative of delta PB with respect to x. So this is our diffusion current equation. We multiply by A to convert J to I, and we evaluate it at x is equal to 0. Now this is where the hyperbolic cosine comes in, since we need to differentiate this whole thing right here. So first we have this Q A dB. So we have already shown that this thing here simply comes from this side, and then the derivative of this thing. So the derivative of this thing with respect to x, everything that is not as a function of x is just a constant. So this is simply a constant. This is simply a constant. So we have here PB naught on both sides. So this term here is based on EQVEB over KT minus 1. This thing is dependent on EQVCB over KT minus 1. So we also need to differentiate this one. Note that the denominator is not a function of x, so it is just a constant. And then the derivative of this hyperbolic sine right here is some hyperbolic cosine, but evaluated at x is equal to 0, then we'll just get hyperbolic cosine W over LB. Now, by chain rule, we need to multiply by -1 over LB. That's why there is no negative sign here anymore, and we get this denominator LB. Now, for this part, we still get that the derivative of this. So the derivative of this hyperbolic sign with respect to x is this hyperbolic cosine times 1 over LB by chain rule, although we need to evaluate it at x is equal to 0. So hyperbolic cosine is this function right here. So at x is equal to 0, we evaluate it at 0. E raised to 0 plus e raised to minus 0 is 1 plus 1 over 2, and that just ends up being 1. By chain rule, this term here appears here, and since we don't have anymore a minus sign by chain rule, then we need to indicate this negative sign from this point. So we now know IEP, which is at this point we next get ICP based still on this delta PB with respect to x, and this is our formula for the diffusion current evaluated at this time x is equal to W. So we actually use the same constants and derivative the same thing, but evaluate at x is equal to W. So now derivative of this is hyperbolic cosine, but W minus W. So hyperbolic cosine of 0 again is just 1. However, at this point, when we evaluate this derivative at W, then we get hyperbolic cosine of W over LB instead. So from those four terms, we already were able to show where this IEN, ICN, IEP, and ICP terms, or derive what the expressions for these currents. We will now proceed and determine the total terminal current. So IE is simply IEP plus IEN. Since this now has been corrected to be on or directed to the right. Okay, so all of these are now directed to the right, and we can simply add them up. So therefore, IE is simply the sum of these two. So now that we have this VEB over EVEB over VT minus 1 term, so we just add these two terms right here. So we have this summation here, and we have this other term right here, which is based on EVCB over VT minus 1. So for IC, we need to add ICP and ICN. So this thing and this thing. So if we write first, so now that this term is a function of VCB. So if we write first the term for VEB, we'll only need to indicate this one. So we have this thing. But for VCB, we have two terms, and both of them have negative signs. So we have this negative sign, and then the two terms. This one is this one. This one is this one. So these are the two same equations we've obtained for IE and IC, but there's just some color coding in place. So these terms here were derived based on the excess hole concentration at the base, and these red terms here as well. So some observations first. So the electron current components, IEN and ICN, are those with factor NE naught and NC naught, and they are the ones in blue. And they are the ones based on the slopes of the carrier concentration at these 2 points. However, the one for the whole, IEP and ICP, are those with factors PB naught. And that is based on the slope of the base or the minority carrier concentration at the base. And say it would look like this one. Now, only current components with PB naught depend on the effective width of the base W and LB. So we have W and LB for these red terms here, the one for the base, but not for the terms related to the emitter and the collector, since W is the effective width of the base. And therefore, controlling W will only affect these factors, but not these 2 factors here. Now, say we want to transform these 2 equations here for NPN. What we'll just have to change is from NE naught to PE naught, and PB naught to NB naught, and NC naught to PC naught, since the minority for NPN is PNP. And also, instead of VEB and VCB, since this is for PNP, we'll now need VBE, so PN, and VCB, sorry, VBC for PN. And also please note that there will be no necessary change in the signs. Now we'll try to simplify the expressions for the currents, which were, or whose complex terms actually came from the excess carrier concentration at the base. However, for real BJTs, we normally design it such that W, or the effective width of the base, is much less than LB to achieve high current gain. Again, LB is the minority carrier diffusion length, and if the depletion, or sorry, if the effective base width is short enough, then the carriers will most likely not recombine along the way, since they recombine average after LB, but you are only giving it W to travel. Now, in this case, if W is much less than LB, and we have this W over LB terms here, so we are actually concerned with W over LB, and if W is much less than LB, then this is a very small number, and the hyperbolic sign of a very small number is approximately that exact number. So this one is based on an approximation if you expand the Taylor series expansion of this hyperbolic sign, evaluated at some very small number. So all hyperbolic signs we can just replace with the value inside it, and so this terms right here we can simply remove. Now note that, for example, this x over LB, x can only go from 0 to W, so the largest is W, but still W is much less than LB, and therefore we can also remove this sign term here and just end up with the value inside the hyperbolic sign. Now in this case, when x is equal to 0, then this is simply W over LB. W is still much less than LB. And if X is equal to W, this is just simply 0 or approaching 0, a very small number. And therefore, we can approximate it or use this same approximation. Now, in this case, since we're left with this one, LB actually cancels out. And also in this first term here. So that's why we end up with this term. So approximately when W is much less than LB, PB naught, this term W over W is 1 minus X over W plus this term times X over W. Now note that this expression here actually tells us that if we design the BJT such that W is much less than LB, then this excess hole concentration is now approaching a linear behavior. So this plot here shows the excess hole concentration at the base for our PNP, and this specific example is for a forward active case where this junction is forward bias and this junction is reverse bias. Now note that this is a bit different from what was normally drawn in the previous slides. So in the previous slides, we were drawing the actual PB. So if we know the PB naught and the device is under forward active, then the plot should be approximately like this. So from something high to something near 0, but the excess here is negative, the excess here is positive. So this is PB, this is delta PB. Now note that we start with some value delta PB at 0 and end up with some value delta PB at W. And note that this term here is exactly delta PB at 0, and this term here is delta PB at W. So if we evaluate this function at X is equal to 0, this simplifies to 1, and this is 0. So we end up with just this term. Evaluated at W, this is 1 minus W over W, so this is 0. And W over W is 1, so we end up with this one. And as shown here, it is linear. And the slope is actually negative, this plus this all over W. Now, we want to get the currents based on this one. So IEP is again this one, evaluated at X is equal to 0, and this one evaluated at W. But since this is linear, then the slope at this point is just the same as the slope as this point, and therefore these two equations will end up to be the same. So note that the slope at the two edges are now the same because W is much less than LB. This approximation leads to a perfectly linear delta PB over X. And actually, if you look back, we end up with such a trend for the excess minority carrier concentration if there is no RG happening. So this is the linear general solution actually refers to when we have this MCDE. Which also tells us that when W is much less than LB, we approximate this behavior where there is no RG at the base region. And therefore, this actually leads to alpha t is equal to 1. Since there is no recombination at the base. Now we look at how this simplification that W over LB or W is much less than LB leads in terms of our current components. So we'll use these simplifications. A while ago we used hyperbolic sign with something very small to approach that very small value. So 1 over this here approaches 1 over this value here. However, for hyperbolic cosine of this variable over hyperbolic sine of this variable, when this is very small, actually leads to this same expression. And we can see that by looking at this. And if we use the same approximations as we had for the hyperbolic sine and for the hyperbolic cosine and hyperbolic sine, for the case when this psi is very small, then we end up with this expression. But if this is small, then this is very large and this is small still, and this will overpower this one, and so we just end up approximately with this term right here. Now for the actual current components, we have this 4 here, although these two are actually the same and does not depend on this one. So there's nothing new with these equations. These two were the ones that changed, and we have here the original expression. And if we follow this approximation, so this 1 over hyperbolic sine is approximately 1 over that thing. So this term or these terms simply are simplified as this one, and this cosine, hyperbolic cosine over hyperbolic sine, simply becomes 1 over the input to them. So we can simplify this 2 as if this one is just 1 and this function as if that function does not exist. So now, since we have 1 over W over LB, so LB can be seen as if it is at the numerator, so that LB will cancel with this LB, and so as this one. And the same thing will happen here. And that's why the LB term was replaced by W. Okay, and the hyperbolic cosine and hyperbolic sine terms are removed. Now say we want to convert those simplified current equations for NPN, what we'll just do is change IEN to IEP, IEP to IEN, ICN to ICP, and ICP to ICN. And for the equilibrium minority concentrations, for P and P we had NPN, so for NPN we'll use P and P, and the voltages should be VBE and VBC, and so we'll end up with these equations right here. So we now have for IEP, we are using PE naught For IEN, we're using NB naught. For ICP, PC naught, and ICN, NB naught. And the voltages of change to VBE and VBC. Now going back to PNP, we'll now use the simplified current equations to determine the BJT performance parameters, although we're actually defining these performance parameters or use them when the device is under forward active. Now specifically what we'll show here is the derivation for gamma for PNP, which is IEP over IEP plus IEN, or IEN plus IEP. So we showed here the currents IEP, IEN, and IEP. Now this is the actual expression we have without any simplification. But this time, since we are dealing with forward active case, then this should be much greater than 1, and therefore we simply end up with this one, QAD over LE and E naught e to the Q VEB over KT. Whereas for IEP, this is the simplified case when W is much less than LB. So note that the denominator is now LB, W instead of LB, and there is no more hyperbolic sine or cosine in both terms. Now note that this factor here is actually the same as this one, so we can just lump them up. And now this minus 1 will cancel with this plus 1, so we can disregard them. And going back to this, since the device is in forward active, then the collector base junction must be reverse biased, and this must be much less than this one. So we can just remove this, and we end up with only this term. So this thing is does not matter anymore. Now, going back to the emitter efficiency gamma, this is the expression, but if we put IEP at the denominator, then we'll just end up with this 1 over 1 plus IEN over IEP, and therefore we need to get the ratio of these two. However, QA is common, and e to the QVEB is also common, so we'll just need to focus on these two. So we have here D over LE times NE naught and DB over W times PB naught, but NE naught is equal to NI squared over NE, but if we say assume or consider the possibility that Ni for the emitter and the base are different, then we can denote that as Nie, and PB naught will be NIB squared over NB. So the final ratio would be composed of D over DB, W over LE, NIE squared over NIB squared, and NB over NE. And so we note here some of the things we can do to improve the emitter efficiency. So we need to make W smaller or much smaller than LE. Again, NE should be very high. We should have a high doping concentration at the emitter than at the base to get high emitter efficiency. And also we can say choose a material that will give us a smaller NIE than NIB. So we need this thing here to be very small. So NIB. So ideally, NIB is greater than or much greater than NIE. And we can achieve this if we have a material such that the EG at the emitter is larger than EG at the base. Since the larger the EG, the lower the NI. But if EG is the same, then NI is the same, or at least for if you have the same material for the base and the emitter, then Ni will be the same and will simply cancel. Now for the rest of the other performance, BJT performance parameters, we have just listed them here, although we'll not anymore show the derivation. So alpha T is approximately this term. So again, if we want alpha T to reach its ideal value of 1, then this thing should be very small, and W should be much smaller than LB to achieve that. Although we are already actually assuming W is much LB in these two cases, we simply include this one to get the first degree approximation for alpha T. So alpha DC is simply the multiplication of gamma and alpha T, and 1 times 1 is simply 1, and so we multiply this term with this term. 1 times 1 is 1, this times 1 is this one, and this times 1 is this one. But if we get this thing squared, we'll get W over LB raised to the 4, and since W is much less than LB, then we just simply disregard that term. Beta DC is alpha DC over 1 minus alpha DC, so we can use this one, although the approximate expression is already given here. Now, similar as to what we have mentioned for gamma, we want W to be very small. Also for these terms here, NE to be much larger than NB, and possibly NIE to be much smaller than NIB. Now, one major difference between this expression here and this expression here is the lack of this one term. Now what happens? This term here should be very small, and if this is very small, alpha DC will approach 1. But for beta DC, if this term here is very small, then without the 1, then this thing should be very large, which is what we want for beta DC. And again, this approximations here is based on the forward active bias case. Now, in the case that we have a narrow emitter alongside a narrow base, when we say narrow emitter, then we are referring to the case when the width E prime is much less than LE. So let WE be the metallurgical width of the emitter, and WE prime would be the when we subtract XP for this junction. And if this happens, similar as what we've discussed for the base, then there should be no, or approximately no, RG happening within the quasi-neutral region of the emitter. So instead of the excess doping concentration exponentially decreasing along x double prime when when the physical width is much less than LE, then they almost won't recombine. And for that very narrow emitter, what we expect is to have a linear change in the excess minority hole concentration. Now, if there is no recombination, then why does this go down to 0? Since we normally have or add there a metal contact, an ohmic contact to be specific, then at the junction, any excess minority carrier concentration will instantly recombine. And so we are forcing this value here to be 0, and it will eventually follow this linear plot. And similarly, like what we did for the base, it actually turns out that we'll just have to replace LE by WE prime. So all LE's in the original equation should be replaced with this new WE prime. So instead of the ratio of W and LE, we now use W and WE prime. Now LB still is maintained as LB, so these are the terms that just changed. So now we'll discuss the ever-small model, again starting from the emitter and collector currents we have derived. So specifically, these equations shown are for PNP. Now for the ever-small model, we actually lump these constants right here as some IF naught, and this constants here as some IR naught. So note that this IF naught is attached to the e raised to VEB term for IE, and this IR naught is attached to this e raised to VCB term for IC, and eventually we'll show that this format here can be modeled as some diode equation, since this is the VEB junction voltage and this is IE, and this is another diode with IR naught as its reverse saturation current, since this is the VCB or CB junction voltage for this collector current. Now, since we have another term, then this can be included in the model as some or using some KCL equation, or to be represented eventually by a KCL equation. And note also that, say, this term here is also this this factor here, and for the ever-small model we denote this whole term here as alpha R IR naught. So this is IR naught, this is alpha R IR naught, and this term as alpha F IF naught, where alpha F is the forward common base DC current gain and alpha R is the reverse common base DC current gain. Now, in our previous discussions, we used alpha as some constant that is around 1 but is actually less than 1, and that can also be observed in these terms. So if this is alpha R IR naught and alpha R is something less than 1, then this whole term must be less than this whole term, which is a bit obvious because of this additional term here. So this whole term looks like this one, but with this additional term, and also this cosine at the numerator is something always, or at least equal to 1. So this whole term is always greater than this one. And the same can be said with these two terms. It can also be observed that this alpha RIR naught is exactly equal to this alpha F IF naught. So for the whole of the ever small model, we actually need 4 constants: IF naught, IR naught, alpha R, and alpha F. Although with this equation, we can just solve for 3 of these parameters and use this equation to solve for the 4th one. So these two terms is equal to QA dB over LB PB naught 1 over hyperbolic sine of W over LB. So these are the same equations from the previous slide, although we already replaced the long constants with IF naught, IR naught, alpha R IR naught, and alpha F IF naught. We make further simplifications. So this we let IF to be this IF naught E raised to Q VEB over KT minus 1. So this whole thing is this thing. So this is IF, and IR is this whole thing. However, note that this whole term also appears here, but with IF naught. So this can be rewritten as alpha F IF, and this term here is exactly IR. So this can be rewritten as alpha R IR, and that is shown in this further simplified equations. Now for NPN, we simply need to replace VEB by VBE and VCB by VBC. But for this equations, this can be used even for NPN, although the change will be internal from these equations. Now, note that from this equation for IE, we can say that this term here is the EB diode current, while this term here is some CB diode current that makes its way into the EB junction because the width of the base is small that the two junctions can interact. In a similar fashion, IC is this whole expression here. The collector current is composed of the CB diode current, which is this one, as a function of VCB, and some EB diode current that makes it to the CB junction. So this is the EB diode current, although not all of it will be able to make it to the collector. Now, all of the equations we have discussed for the ever small model can be represented by this equivalent circuit. So if we look at IE, IE is composed of this term that looks like a diode, which is exactly equal to IF. And it is dependent on some voltage VEB. So we orient the diode with the P side at the emitter and the N side at the base, which also makes sense since this one is a PNP model. So this diode here, or this diode here, it came from this one, and this diode here came from this one, PN. And this IR is represented by this equation. Although note that IC is rightwards, but this IR is leftwards, so that's why it's called the reverse current. So again, the diode currents IE is rightwards, IC is rightwards, IB is downwards. Now, if we again look back on this one, the other term is subtracted, meaning its direction is the opposite of IE. So that's why we draw this current-dependent current source to be opposite of IE. And then for IC, we have this term here, which is positive, so its direction is the same as IC. Now, by KCL, if we focus only on this shorthand notation, we can say that IE going in is equal to IF minus alpha or IR. So it is consistent with our expected equation. And for IC, the KCL at this node, IC is equal to IR minus alpha. Sorry, IC is equal to alpha FIF minus IR. So this one is consistent with our KCL at this node. And since this diode has a voltage across it, VEB, we can just say that its reverse saturation current is IF naught, and the reverse saturation current of this is IR naught. Now, to remember this symbol, just follow the diode orientation based on the structure of the device, and then the current-dependent current source should be in the same direction as to the one it is paired with. And on the same side, there must be opposite directions of the current. So for example, if we draw the ever small model for an NPN, let me draw also its symbol here. So IE in this case is leftwards, IC is leftwards, and IB is upwards. If we start with the diodes, so we have PN and then PN, both directed outwards. So we can draw something like this. And if this side is connected to the emitter, then we can define this one as IF and this one to be IR. However, note that IE is leftwards, as well as IC, and that is consistent with our drawing here, with our symbol. Now we can draw the current-dependent current sources. We have two of them. But for the emitter side, we will draw it in the opposite direction and opposite direction as well at the collector side. Now we can label them as alpha. So for the emitter side, that should be alpha R IR. And for the collector side, that must be alpha F IF. So these are the forward terms, these are the reverse terms, and to complete, IB in this scenario is upwards. So still we will be consistent with this equation. IE is equal to IF minus alpha IR, and IC is equal to alpha F IF minus IR. If we assume now the forward active case or approximate for the forward active case, we know that the CB junction must be reverse biased, and if we draw again the diode, the reverse diode for this PNP ever small model, since this diode is reverse biased, then we can approximate it as an open circuit. And if we do that, then IR is approaching or approximately 0. And if IR is 0, then alpha R IR is also approximately 0 or even smaller. And so we just end up with this model right here, which is what we call the T model, since it looks like a letter T. Now for NPN, we have this equivalent model right here, and what we are left again are the forward the devices corresponding to the forward currents. Now for the forward active case, the reverse or the CB diode is reverse biased, so this one is 0 as well or open, but the emitter junction is forward biased. And if this diode is forward biased and we use our previous approximation for forward biased diodes, then for this NPN, we'll just end up with this circuit. Which should be familiar as we have used this in our BJT circuit analysis. But instead of writing it as alpha F IF, we write it as beta IF, where in this case, IF is now approximately IE, since this one is open. And IC is approximately alpha F IF, since this one is open. So again, in these models, we approximate that IR is 0. So here IR is 0, and here IR is 0. And since IR is 0, alpha IR is approximately 0. And what will be left with IE is IF. And IC is alpha F IF. So in summary, we have outlined how the MCDE can be used to analyze BJT currents under different biasing conditions. And we assume that there is no recombination in the quasi-neutral regions or at the depletion regions, and there is LLI conditions prevail, and also specifically for the base, there is no RG, and that is achieved when W is much less than LB. So the base region must be very thin compared to the base minority diffusion length. As we have shown, the BJT parameters can be improved by these relationships. So W must be much less than LB, W must be less than LE. So this one also helps. Having a very high doping concentration at the emitter helps. And we can also make NIE to be smaller than NIB, and this can be achieved by using a material that is or that has a larger EG at the emitter. Now for the ever small model, we have shown how it can be used to model the BJT with 2 diodes and 2 current-dependent current sources, and the 4 important parameters for the ever small model are IF naught, IR naught, alpha F, and alpha R. Although a word of caution, although this looks like they are some constants, they are actually dependent on the biasing condition, since W appears in this constants or quote-unquote constants, but in reality W depends on the bias voltages, since W is a function of the depletion current widths, which depend on the bias voltage. So that's it for this lecture. Thank you very much.